Hello world, I'm Christopher Magashek, and today I will be showing you how I programmed an encrypted message exchange simulator. So what this is it basically simulates two people sending messages to each other by encrypting their messages and then uh, submitting them to a public network so that they can decrypt it from there, as well as a third user, a man in the middle, trying to intercept those messages and decode them. Um, And a little bit of background for this program is that in my final semester at ODU, I had a cryptography class, and they gave a semester project, and the project was either to write a 10-page paper on something cryptography related or to make a program about something cryptography related, and it could be anything we wanted as long as it got approved by the professor. So um, I decided to make this. I decided to make this program and simulate, how things are encrypted and the vulnerabilities as well. So without further ado, let's choose the encryption method. So we were taught about five main encryption methods. Are three asymmetric encryption methods: RSA, ElGamal, and elliptic curve cryptography. And then like two symmetric encryption methods, DES and AES. I really only had time to implement RSA and ElGamal, which I feel was more than enough. Um, but I also decided to add Caesar cipher and add bash cipher as well as plain text. But yeah, let's choose RSA encryption. That's the one people are most familiar with, the one where you hack into it by factoring large integers. Which block cipher mode of operation would you like to use? So what that means is, since messages are variable length, you have to split your message into chunks, into blocks, and then encrypt each block separately. But if you do them all independently of each other, which is called electronic codebook, then that basically that can be hacked, but that can be you can crack the code using probabilistic methods such as like a crypto clip, like on the newspaper. Um, so it's better to like have each different block encrypted using a different method or encrypted slightly differently, and that's what you do in Cipher blockchaining mode. It's also what happens in Outbook feedback mode and Cipher feedback mode. But the problem with these two is they aren't really compatible with asymmetric encryption, which is basically this simulation is basically only doing asymmetric encryption, and so these two aren't really compatible with that because the public key is used to both encrypt it and decrypt it. The private key, you do not need them at all for these two methods. So let's go with Cipher blockchaining mode, CBC. And lastly, would you like to use signatures? Yes, I would. That's something that's used to help verify the identity of the sender. More on that later. So at the beginning of the simulation, you start out as Alice. There are three people in this simulation. There's Alice, Bob, and Charlie. Alice and Bob being the two people sending messages to each other, and Charlie being the man in the middle who's trying to hack into them. But you start out as Alice. You're seeing everything through Alice's eyes. There aren't any conversations yet, so let's make one. Let's send a message to Bob, saying, "Hi, Bob. Long time no see. Weird weather we've been having lately." All right, and and we can actually read the conversation. So the thing is, we read Bob. Yeah, so we can see the message we sent. And every time we send a message, two things happen. First is that we save an unencrypted copy to our local device. What that means is, or the simulated local device. So what that means is it's a copy that only the sender can see because they didn't submit it to the public network. And then after that, they encrypt it and then send that to the public network. They encrypt it using, this is asymmetric encryption. So you encrypt it by using the receiver's public key, and then the receiver decrypts it using their private key, and so that helps keep it secure. But anyways, so what we're seeing right here is just our saved copy because we can't actually decrypt what we sent. We were only able to encrypt it. But anyways, let's change role. Let's change users to Bob, and so now we're seeing things through Bob's eyes. And would you look at that? We got a new message. Um, one unread from Alice. So let's see what Alice said. Hi, Bob. Long time no see. Weird weather we're having lately. Yeah, let's respond. That was pretty nice of her. To Alice from Bob. Hey, Alice. Yeah. So yeah, we sent a message to Alice, and as we can see, yep, it's been sent. So we switch roles to Alice. One unread from Bob. And that's nice, he replied. This is all pretty good and all, but let's actually, this might as well just be message exchanges, but well, let's actually show the encryption part of this. So, for one thing, this is something everyone can view, regardless of who you are, is you can view all the messages encrypted in their raw text form. Um, I like how this one, it couldn't even render the characters that it created, because they're not legible characters. Um, but yeah, and then we have the initial value and the signature included. Anyways, let's change roles to being Charlie. Charlie, the man in the middle. Uh, so we want to try and view the messages that got sent between those two, and we could just scroll up and see them, but see that's against the rules. Okay, we're supposed to be seeing this from Charlie's eyes. Charlie can't see their messages unless he sees their messages himself. Um, so that doesn't count. That's like, but anyways, let's try read conversations with Alice. Nothing from Alice. How about with Bob? Nothing with Bob. Well, okay, let's just view. We can just view what's on the network anyway, though. But it's all encrypted, and we don't have the decryption keys for either of these. Um, so how do we see what they send each other? Well, we're gonna use our hacking tools. So we have Snoop, Spoof, and then the ability to like save and edit keys, as well as a few math tools. We'll get to that in a bit. So what we can do here is there's this interface was built in that allows us to if we happen to discover someone's private key, then we can sort of save it and then use it for later. So if we try and using Snoop, it basically asks, okay, did we at some point save their private keys? If not, just show it as is. Unless it also has to ask, did we perchance save these messages to our own device? Which of course we didn't. We're not the sender of either of these messages. So we don't know the private keys, but we can reverse engineer them because the thing is, the private keys for these are 32-bit. In most real-world applications, you use quite a bit more bits. That you usually use at least 1,024 bits. But here we use 32 bits, and I'll explain the reason for that later. But that makes it a lot less secure and much easier to reverse engineer the private key. So let's use some math tools to figure this out. It shows the public keys, but it also shows Charlie's private key because of course Charlie knows his private key. It's literally saved to his device. It's not available to anyone offline, but but it's not available to anyone online. Excuse me, but it's available to Charlie offline. But anyways, let's use these math tools. And so what we're going to want to do is first of all we're going to take the modulo. So whose private key do we want? Do we want Alice or Bob? Let's say eeny meeny. Let's say Alice. Okay, so we're going to want Alice's private key. So first thing we want to do is we want to factor this number. We got prime factor of 118 722 5. I wish I could just copy paste this. That would make it a lot easier. All right, and let's factor that. And then now what we want to do is we want to compute the totient. Specifically, we want the Carmichael totient, as opposed to the Euler totient, which I had already implemented. But anyways, we take the Carmichael totient by taking these numbers, subtracting 1 from both of them, and then finding the least common multiple. So 25056 and 47380. All right, so that's the totient. And now what we want is we want to take the modular inverse of the second part of the key, which is 65537. We want to take the modular inverse of the exponent with respect to this totient. So 296788320. Yes. And that is Alice's private key. Assuming I did everything right. So let's go back and try to save Alice's key. Alice's key is 99927 233. Yeah. And notice it didn't tell us if that was correct because it has no idea. Only Alice can see her own private key, so we just have to take our word for it for this. And let's see if that's right. We snoop. We can't see the message Alice sent to Bob because that's encrypted with Bob's key, but we can see the message that Bob sent to Alice. So yeah, and this appears to be correct. That or it's just a massive coincidence, which is pretty unlikely. So yeah, we were able to decrypt the message to Alice, and let's see what else we can do. So something interesting is that what you can do is if you're using the receiver's public key to encrypt your message, and then they use their private key to decrypt it. There's nothing in that process that prevents you from pretending to be someone else when you send a message. And so in order to counteract that, what you have to do is use signatures. A signature, you take the hash, and then you use your private key to encrypt that hash. You take a hash function of the message, I should specify. You encrypt it with your private key, and then everyone else is able to decrypt that or anyone else can decrypt that hash, that encrypted hash with your public key, and then see if that matches the hash of the message. And so that's how you verify authenticity. So let's see, we have Alice's private key, but we don't have Bob's private key. So let's start by sending Bob's private keys as a control group. Sorry, Bob's snooping Bob as a control group. So it's to Alice from Bob. We're going to say, you stink. And then we're going, let's go back and switch roles to, was it, yeah, okay, so I switched to Alice. Ooh, that's nice. One new conversation. Who is it from? It's from Bob. Let's see what they said. You stink. Oh, that's not very nice, but what's that? It's spoofed because the signature is not correct because we didn't have Bob's private key. But by contrast, let's go back to being Charlie. Go back to hacking tools. We can spoof to Bob from Alice. And since we have Alice's private key, we can successfully spoof without getting caught. So, to Bob from Alice, I hate you. And we can go back, switch roles to being Bob, right? And what's that? I got a conversation. It's from Alice. I wonder what nice things she said. I hate you. That's not very nice, and it's an authentic message. Why would you say something like that? And what's interesting about this, actually, is that if we switch roles to being Alice, and read conversations with Bob, we never stored that message, the one that says, I hate you. So we have no idea that someone pretending to be us sent that message. Actually, the only indication we have is that if we checked the encrypted messages and noticed that there was an extra message we didn't send. That's the only indication we have. And so we could tell Bob, hey, someone sent a message pretending to be me, but what we can't tell them, we have no idea what the message says, because this is just a bunch of nonsense. And it's encrypted using Bob's key. So the best we can do is send a message to Bob saying, hey, sorry, I think someone sent a message to you pretending to be me. I have no idea what they said, but please disregard it. Thanks. Cool. And so we changed roles to being Bob. There's a new conversation with Alice. Ugh, I don't really like Alice. But let's see what they said. Oh, hey, it was all just a big misunderstanding. Okay, that's good. So yeah, that's basically how this works. Um, it was a lot of fun to make this project. Um, let's see, we can view public keys at any time. Um, hacking tools, admin. Admin is so these are things you actually wouldn't be able to do in either of these roles, but they're more so ways that you can edit the simulation. So you might have noticed that at no point in the simulation was it only Charlie who was allowed to hack. Anyone could hack anyone, and anyone could send messages to anyone. Um, that's just the way that the code was written. All users are on equal ground. And also, I also added more tools in case you wanted to edit the simulation. Like, what if you wanted to have 4 people or 5 people? So you can add users, or remove users, or change their names. So, for instance, let's say uh, Charlie. What if we want to change Charlie to Carol? We go back and we can change roles to Carol. I am Carol. And we can view conversations with Alice. It says right here we sent a message to Alice pretending to be Bob, and it says that it was spoofed, which we know because we were the ones who spoofed it. We're the only ones, or sorry, this one was done with a bad signature, but with read conversations with Bob. This one was sent with a good signature. We're the only ones who were notified that this is spoofed because we're the only ones who know it for sure. Other than, I guess, Alice. But anyways, so yeah, this was a lot of fun to make. Oh, there's also settings as well. Raw text mode. So when you see the encrypted messages, it displays them as a bunch of characters. But there's also the option to display them as like decimal numbers or to display them as a hex dump. And then this one right here, when you ask to see the public keys, this option determines whether or not it also shows your private key among that. I just felt like that was somewhat important. But yeah, let's actually show how this code works. So let's see. So at the core of this. Oh, and first things first. Let's, in case anyone was wondering. So I sort of kind of took this code from the internet. This right here, the change delimiter. So you might have noticed during the code that when you send a message to someone, you can use spaces in that message. But when you're like, for instance, when I used the math tools and took like least common multiple, space was used as a delimiter between the numbers. And so the way I was able to do that was I sort of kind of took some code from the internet that I didn't fully understand, but I understood it enough to edit the code and make it what I wanted. So basically, I used these two things and then plugged them into this function, allow spaces, which at the bottom we see true makes it so that space is not a delimiter, false makes it so it is a delimiter. And so just in case you were wondering that, I felt like I'd get that out of the way immediately. But anyways, so at the heart of this program is the message. So what's important on the message? The message has a sender, a receiver. It has the content, which is stored as a stream of 32-bit integers, and I'll tell you why it's 32 in a bit. We have the initial value, the signature, which the signature can be is stored as like an array of 0 or more integers, because you could just have no signature. You could have that disabled, or sometimes you need multiple components to actually store the signature. We have the length of the string, the length of the array after the string's been converted to an array, the length of the signature, and then the length of this extra thing, which in case there's any extra information you need to store, I made this variable. For some reason, I made it public. We also have Boolean red, which is literally just That's how I was able to show that thing. You have like three unread messages. This just determines if a message has been read or not. So let's see. We have this. This determines if it's to and from given people. We have the getters, encryption and decryption. We'll get to that in a bit. Sign and verify sign. We'll also get to that in a bit. Make header and raw content. Those display the header to blank from blank, and then the raw content displays the raw content. So we can see how those two work. This one, it can either display it as a string, or as an integer dump, or as a hex dump. So as initial value and signature. I guess it didn't. It doesn't display the extra part. I guess I don't know why it doesn't do that. I guess I just forgot to add that. But let's see, encryption and decryption. We'll have to get to that in a bit because first we have to explain the underlying structure behind this. So we have the user. Each user is unique. They have, let's see, what components do they have? They have a name, of course. They have a private key and a public key, which are potentially multiple 32-bit integers. They're all unsigned, by the way. We have the size of the private key, the size of the public key, and then here's that thing I mentioned before where you save a local copy of any message you send. And technically there are multiple ways of doing this, but in this particular case, this just seemed like the best way to do it. And also secrets, because I mentioned that you can store someone's private key or what you think their private key is, and store that for later. And so this is the array. It maps a user to their supposed private key. And here we have a bunch of functions that work with that. Save secret. I refer to the person whose private key we save as sucker. I think like in my head I said the sucker will be none the wiser, and that just kind of stuck with me because I thought it was funny. But anyway, so we save the sucker's secret. We can remove the secret if we think it's wrong or if we don't want to have it anymore. And then here, I don't know why this got grouped with them. Determines if a message has been saved. Oh, also the current user. This is actually very important because we have the getter for the public key. The get private key, I actually implemented like a failsafe to make sure I didn't accidentally give other people the ability to view someone else's private key. This was also as a show of good faith for the teacher to show there wasn't any funny business here. It literally checks, is this the current user? If not, I want you to crash the program so that we cannot continue. Because you can only see someone's private key. At any point, you should only be able to see someone's private key if that someone is you. So, yeah. I probably should have also done the same thing for the saved messages. That would have been a good idea. But anyways, let's see. Push message, load message. Generate key. Again, we'll get to that later. Oh, and then the greet, the thing that says, "Welcome, Alice." But anyways, so here we have all that. Discrete. Okay, so here's where we start to get into the encryption and stuff. So, I need to plug in my device. So we have discrete problems, and I should just show like the code as is instead of the header file. So we have GCD, and this is sort of a fusion between code I found on the internet and code that I wrote myself. I've made this and fine-tuned it over the years, but I sort of got the idea from someone online. It's similar to the Euclidean algorithm, but instead of like dividing and then like subtracting and then dividing and subtracting, instead we only do this through a combination of subtracting the two numbers and then right shifting them. And so that makes sure there, and also this converge, just like the Euclidean algorithm, this converges big O of log n steps, so it converges pretty fast. And I would explain this, but I feel like, I'm already going to be spending a lot of time explaining everything else. In fact, I haven't checked yet, but it's probably been a long time since the start of the video anyway. But anyways, you probably know LCM, least common multiple, is just the product divided by the GCF. we have modular product, and this is where I'm going to explain finally why these are 32 bits. So originally for RSA, I wanted it to be like I was originally thinking, okay, I'd have two 64-bit prime numbers and I multiply them together. Oh wait, that's not going to work because that's going to be a 128-bit number. Um, so I was like, okay, fine, I'll have them be two 32-bit numbers multiplying into a 64-bit number. And that was kind of what I went with for a while until eventually I realized that's still not going to work because modular multiplication, in order to multiply two things modulo a third thing, um, you have to multiply them and get a number potentially bigger than the third thing. And then after that, modulo it with a third thing. And it could be potentially like twice as many digits, even. And so that sort of creates a huge problem because if the modulo is 64 bits, then you could potentially get something up to 128 bits before moduloing it with it. So finally, I realized, okay, we need the things we work with to be 32 bits so that modular multiplication works. We cast them to 64 bits, multiply them together, modulo the third thing, and then cast them back to 32 bits. And so that's what I went with. And so that also means the primes in RSA are two 16-bit numbers. Modular power, I actually also kind of had this code lying around as well. Um, it uses exponentiation by squaring. I would have used two to the p area, but that's kind of complicated. So let's this works good enough as is. It's already big O of log n things anyway. You just analyze the binary digits. So it's pretty good, and it's got optimizations in it as well. Like like this thing right here, where instead of you see, okay, is this thing one? If so, set it to this. Otherwise, multiply it by this. Um, yeah, and then also making sure not to multiply if this is the last iteration. Um, yeah, I've had this code for a while. I've had plenty of time to fine tune it. Bazal, Bazal's identity. That's actually the extended Euclidean algorithm. Is solving Bazal's identity. Ax plus by equals the GCD of a and b, and then you're solving x, y, and that GCD. And this one is just flat out the extended Euclidean algorithm. There's no fancy bit shift stuff. Um, yeah, I don't see any. And so yeah, and also potentially you might have to negate some of those values at the end. That's why it's a long. It would have been like a 32-bit integer, but then I was like, ooh, but the numbers could be negative, so signed 32-bit. But then I realized, ooh, I can't do that because it could overflow by literally 1 bit. And so I literally have to do a long, adding an extra 31 bits just because that's how it needs to be. So we have a signed 64-bit for this, or 64-bit array rather. It's not really a big difference anyway. Discrete root. So this one um, ends up using the prime factorization, but to be fair, you prime factor the totient, which is usually a lot easier than prime factoring like the original modulo. If the modulo is like if it's like a prime or a product of two primes, the totient is usually like divisible by a lot of things. Usually, at least, at the very least, it's much more composite than the original number. There's probably a more efficient algorithm somewhere out there, but I think I struggled to find one. Um, because this was sort of a race against time. So the thing with the project was before in the semester I had already messed up on one of my assignments, and so to make up for it, I wanted to really do my best for this assignment because this was worth a decent portion of my grade. And so that's why I really wanted to give it my all for this assignment. That's why I went above and beyond. Um, let's see. I actually, so what was it? It started with one day. I just spent a little bit of time making the message and user classes, and then like later I spent like a solid like 10 hours straight programming. I was just completely in the zone that day, and then I did a similar thing another day, And then finally on the weekend that it was due, I just spent like 2 days continually working on this assignment, as well as another assignment that was due that was significantly less complicated. And I think during that weekend, like only a few hours into that weekend, I had already reached the point where I was like, okay, um, even if I turned in what I have now, it would still get a good grade. But so at that point, I was just working. I was just adding all the things that still wanted to add there, which was ElGamal and then the signatures. Um, so yeah, I actually got 100 on this. I was actually kind of expecting that I would get like possibly even extra credit for this because of how above and beyond I went for this. But 100, you literally can't ask. It's unreasonable to ask for anything more than 100. So I was pretty happy with this. But anyways, so we have primitive root, which is important for the ElGamal encryption. Um, and I could have probably found a more efficient method out there. I probably could have, but um, honestly, my time would have been much better spent doing other things, like, working with signatures. Make generator. So we literally just like generate random numbers until we find one that's a primitive root. Um, and this is also important for ElGamal. Also, the thing we're trying to find a generator for must be prime. Um, let's see. Modular inverse just uses Bazal's identity, and if the GCD isn't one, then we throw an exception, which I think potentially will just get caught. And it'll just like print it out to the console and say there's no modular inverse. But anyways, next we have modular division. This was actually um, so at some point decided to implement the discrete logarithm because that's important for hacking into ElGamal encryption. And originally I was going to use what is it? Pollard's row algorithm. But then when I wrote it, it only worked basically 50% of the time. And because I didn't actually understand the algorithm, I was just like copying what I saw on Wikipedia. I couldn't really troubleshoot it. So instead, I got stuck using brute force, which is big O of n instead of big O of square root of n. Today, I actually do understand the baby step, little step algorithm, and so I probably could have done that. It's actually not that complicated, but I guess my time was just better spent doing other things because this really was like a race against time. Even towards the end, when I was just implementing features I really wanted to implement. Um, let's see, but yeah, we have. It also should be mentioned that when I turn this in, let's see, where do I have this? I have right here it is. Here it is. So yeah, this was I made sure to write like a document explaining what to do here. I didn't just to let the professor just figure it out herself. I made sure to include instructions on like how to hack into the users and what you're actually doing here. Um, but yeah, anyways, back to this modular division. Had I implemented the Polar row algorithm, this would have been important because it would have returned all of the solutions to A over B. Because like if A and B aren't co-prime, then there could be zero solutions or there could be multiple solutions, and so this returns all of them. Let's see, is prime. I know for a fact this one is definitely not the fastest because what you actually do in real life is there are these probabilistic primality tests, which means that technically you'll never be 100% sure that it's prime or not prime. Um, or sorry, you'll never be 100% sure that it's prime. Excuse me. Um, but like as you do more and more iterations, the probability that it's not prime gets smaller and smaller. And so, but this one is literally just doing a prime factorization and then like seeing if it's empty. So it's very slow. Like if these weren't 32 bits, this would literally generating the key would have been just as slow as trying to reverse engineer the key. So yeah, in hindsight, this is a very inefficient way of doing it. But at the same time, I didn't want to take any chances and accidentally make everything break. Um, like I really wanted to get a good grade for this, so I ended up doing this instead. Random prime number. You literally just generate random numbers in the given range, and then And then, just do that over and over until you find a prime number. Prime factorization. This is something that I definitely had lying around. And let's see. So first thing you do is you factor out 2, 3, 5, and 7. And originally I actually had it so these were done with modular inverses to speed it up slightly. But that was done in Java where everything was signed. Here things are unsigned. And so I would have had to like change the formula slightly. And so I decided that's not really worth my time. So because again, I was on a crunch to implement things I really wanted to implement. So instead, I just decided modulo 3 divided by 3, modulo 5 divided by 5, etc., etc. But anyways, after you factor those out, you next see if the number is 1. If it is, then you're done. Or sorry, if those were the only factors, like if you after dividing them you only have 1, then you're done. Otherwise, you perform a loop up until square root of f, looking for factors. When you find a factor, you divide your number by that factor and then recalculate that square root. So now you have to search an even smaller domain. And then this right here, so the thing is, a well-known optimization is that if instead of searching through all the numbers after that point, up until the square root of f, if instead you only search the odd numbers, then that cuts down 50% of the search space. And so I sort of took that to another level. I was like, well, if I also cut out all 3 of the numbers, then I only have to do 1/2 times 2/3 is 1/3 of the search space. If I only check numbers that are either 1 or 5 modulo 6. And so then I decided to take that to also checking for 5 and 7. And that cuts the search space down to about 22% of the numbers in that range. 22, 23. Um, but then the catch is, in order to cut those down, you're like, well, okay, so I just have to 2 times 3 times 5 times 7, that's 210. I just have to make sure the modulo 210, it's not, something that's, it's not, I have to make sure it's the correct thing modulo 210. But if you're doing a modulo, that's not really saving you on any divisions. That's just, you are already going to do a modulo. And so that's not really saving you anything. So what I instead do is I like have this weird thing of code where like we have this variable option. It's a byte. I figure there's 256 possible values of a byte, 210 possible values of this modulo. So this will kind of encode what we are modulo 210, and then depending on what that is, we determine how much to increase n by 2, 4, 6, 8, or 10. And then also, I didn't have to so let's see. This is a total of what is this? 18, 19, 20, 21, 22. Technically, it would have been like 40 cases, but due to the symmetry, due to a certain reflective symmetry, it's actually only about 20 cases, and that's also why this happens here. It has to do with like a reflective symmetry across modulo 100, across modulo 210. Very difficult to explain, but basically this ensures that we only look at certain numbers which are guaranteed not to be divisible by 2, 3, 5, or 7. And I did my best to explain how this works, which, to be fair, I guess that time could have been better spent doing something else, but whatever. Let's see, we have the totient, which basically, this is Euler's totient. You can look up how that's calculated. Factor to string. Yeah, that's right. So the prime factorization, it returns a map from 32-bit integers, the prime factors, to 32-bit integers, the factors exponents. And so this takes that and then converts that into like a string that actually tells you the prime factorization. And that's very useful in the hacking interface. We have the discrete logarithm, which again I said was done through brute force, which makes it very slow. You'll see that in a bit. And then we have string hash, which what is that? That's right. That's the when you're taking the signature, you have to hash the string. And I literally just decided to use Java's hash code function, where multiply by 32 by 31, add the next number, add the next character, excuse me, etc., etc. Next we have BMOP, which is block cipher mode of operation. So this determines how the blocks are individually encrypted. We have an enum, which encodes one of four different types: ECB, CBC, OFB, and CFB. There's also counter, which that one was just a little bit too complicated. I decided not to implement that one, but it is. I hear that's. I'm pretty sure from what I read it in the textbook, it's a lot more. It's much better than the other ones, I think, if I recall correctly. Also, for some reason, I decided to group into the BMOP class the functions that convert strings into an array of integers, and then vice versa. Um, but then we also have these functions which, do all the. Let's actually look at how they work. So, string to array. So the thing is, there's this variable group right here, which tells you how many characters to group into each integer. Originally, I was gonna have it so 4 bytes in a 32-bit integer, and they're each character is 1 byte. I'll just put 4 characters in each integer. Then it turns out, no, you can't do that because potentially those 4 bytes together could be bigger than your modulo. Because this is all about modular arithmetic. And so if it's bigger than the modulo, then there's a bit of ambiguity if the number is the original number or if it's the number minus the modulo. And so in order to fix that, I instead of had it so there's 2 characters per 4 byte chunk. So two of the bytes are literally just to make the math work out, and so literally doubling the size of the message by encrypting it. But that's fine. To be fair, I could have had it grouped by 3. Like with the way the code was written, there'd have been absolutely no difficulties changing the grouping to 3 instead of 2. But I guess I just didn't do that. Um, but let's see. And then this converts arrays back to strings. Again, given the grouping, which is set to 2. ECB, electronic codebook. Like I said, you literally just encrypt them one by one. CBC. So there's 2 methods. One is for encryption, one is for decryption. So each iteration, you take X and XOR it with you take your current integer, XOR it with the previous encrypted integer, and then encrypt that. And then to reverse that, each iteration you take this and then XOR it with you take the previous y value and XOR it with the decryption of the current y value. Because XOR is itself inverse operation. We have OFB, which I'm not going to explain how all these work. But I should note that CFB, like literally within hours of turning in the project, somehow CFB just stopped working. I don't know why. It didn't work. Um, and so I just decided okay, we'll just leave it be. I didn't realize it until like literally like shortly before I turned this in, so I just decided to say that in the document. I was like, okay, uh, CFB doesn't work. Sorry. Um, and then this function, like I said, CFB and OFB, those use the encryption key for both encrypting and decrypting. So this sort of reflects that. This tells you about that. But anyways, let's see. Next up, we finally talk about the way that everything's encrypted. But first things first, we need to describe how the keys are generated. So user, that's where it is. So we have generate key RSA. So what you do first is you generate 2 random prime numbers, 16-bit, and then you multiply them together to get your modulo. You find the totient by you want the Carmichael totient because that's usually a little bit better. By LCMing p minus 1 and q minus 1, you get the exponent, which for some reason by default, like in most operations in real life, it's usually 65537. But then if that doesn't work, then like if for some reason it's not co-prime with the totient, then you pick another one. In this case, I just increment it until it's not co-prime with the totient anymore. Um, I should probably have it. I probably should have had it increment by two each time because um, I guarantee you, if the exponent is divisible by two, if it's not odd, then it's definitely not going to be coprime with the totient because the totient is definitely going to be even. But anyways, oh, and then we find the decryption key by taking the modular inverse of e with respect to the totient because that's how taking the nth root modulo n works. Um, is similar to raising a number to the power of one third to take the cube root. You raise a number to the power of the modular inverse of 3 to find the cube root modulo n. Although you instead of modular inverse mod n, it's modular inverse mod the totient. But anyways, we record the public key, which is the modulo and the exponent, and the private key, which is the inverse exponent. We record the private key, and then we save the secret because of course, we already know our private key, so we're gonna save that. Um, and then ElGamal. So this ElGamal is quite a bit more intricate than RSA encryption. To the point that I had to like write a cheat sheet for myself to make sure I got the facts right. So what is it? First things first, you take Q, which is prime. You find a generator for it, something where um, for every for every number coprime to Q, which is just everything but zero, there exists some number that G can be raised to the power of to equal Q. So we have to make a generator for Q, and then X is just some random number between 1 and Q minus 1. So literally any random number modulo Q that isn't 0. We take H, which is the generator to the power of X mod Q. And that also means, so X is part of the private key. So that means if you wanted to find X, you literally have to take a discrete logarithm. Find the logarithm of H base G modulo Q, which is just as hard as taking a prime factorization. Um, but anyways, then we store the public key and the private key and save the secret. I also did generate key Caesar. The Caesar cipher, if you don't know, you're literally just, like, for instance, if your shift is 1, then A becomes B, B becomes C, C becomes D. Um, if your shift is -1, then A becomes Z, B becomes A, C becomes B, etc., etc. So we literally just pick a random integer between 0 and 26. Um, and then that's that's the private key. Or it's the private key and the public key. Or sorry, the public key is that, the private key is the negative of that. Unless it's 0, then it's also 0. Sorry. It's not the negative. Well, it is. It's 26 minus that. Unless it's 0, then it's also 0. But anyways, whatever. And then for none, there's just nothing. Um, but anyways, so that's how we generate the key. And then what does the message do? The message also has encryption, which, yeah, so literally you determine the parameters for encryption. And here's where I should probably mention, this was my first time using lambda functions in C++. It was pretty fun. I'd used lambda functions in Java before, because that's my main language, but I hadn't done it in C++. And so this was my first time. It was honestly pretty fun. So you generate functions from the block cipher mode of operation, and then use those to call upon encryption functions from the encryption.cpp, which we'll show very, very soon. Um, but yeah, so we determine the parameters for those functions, given what method we're using. Um, and we also determine the random value. And this is where it's probably a good time to mention, this is something that I modified after I'd already turned in the project, because there was this rare bug where occasionally you'd send a message, and then when it gets decrypted, the first two characters in it were completely messed up. And for the longest time, I didn't know why that was the case, but it was very rare and very subtle to pick up on. And finally, eventually, I realized, oh, it's because the initial value, if the initial value is too big, then it could, even though the character is restricted to only, the 2-byte integer limit. The initial value wasn't, and so their XOR also wasn't restricted to that, and so that's what messed everything up. Um, and so I fixed that so that it originally just said random, and so I changed that to be random ampersand um, uh, 4 zeros and then 28 ones. But anyways, I just felt like I needed to point that out for full transparency's sake. But anyways, let's see. So we encrypt it. Um, we generate the message from the encrypted thing, and then if this is ElGamal, then we have to save an extra bit of information, which we'll talk about in a bit. And then for decryption, we just generate parameters from our mode. Uh, um, and also, it's important to determine whether or not we need the decryption key to decrypt it. Um, yeah, basic stuff. We also have the sign function and the verify signature function, which I like how I didn't notice until recently that no matter what the encryption method is, we just set the parameter to the public key. Okay. I probably should have included more comments on this in hindsight. Um, Actually, on a lot of things here. Anyways, so now that that's done, let's finally talk about the encryption scheme. Um, let's see. So first we talk about RSA. RSA is extremely simple. All you do is take the input, 32 bits in this case, raise it to the power of the exponent, modulo the modulo, and that's how you do it. And RSA encryption is the exact same as RSA decryption. It's just that instead of raising it to the power of that exponent, you raise it to the power of the modular inverse of that exponent, modulo the totient. I know this is a lot for people who aren't familiar with like cryptography or who aren't familiar with modular arithmetic, but just take my word for it. ElGamal encryption. This is so we have to take a look back at this document. Um, okay, so let's see. We take y was a number that was randomly generated when we generated this message. And in actual ElGamal encryption, what you want to do is you want to generate a different y for each block. But that became extremely hard to implement, and so instead, I just had it be different for each message, and I figured that's good enough. Um, and also for the same reason, that's why if you try and use OFB or CFB while in ElGamal mode, it's just not going to work because it has no way of knowing what Y is. Um, so yeah, that's unfortunate. Or maybe it's just there's a bit of extra piece of information that gets randomized with every message that it just doesn't know how to work with. It's kind of hard to explain. Um, but anyways, so next thing we do is we take S is equal to h to the power of y mod q, and then we multiply that by our message, um, and then return modulo q, and then return that. Um, I like how right here, this I should have used the modular product for this, but I guess I wrote this code before I had the hindsight to write a function called modprod, uh, instead of just having to painstakingly write this stuff out. I guess I just forgot to do that. Um, Keeping my code wet, I guess. But anyways, so let's see. So you multiply by that and then return that. And then to decrypt it, so the way this works is actually it's very similar to the Diffie-Hellman exchange, whereby you raise the power of A and then raise the power of B, and it's the same as raising the power of B and then raising the power of A. It's a commutative thing. Um, and this sort of relies on that. So to encrypt it, you take h to the y times the input. To decrypt it, what is it? Um, what is it? So okay. So C1 is equal to the parameter 3, which is what is that? Oh, Oh, okay. Parameter 3 is. Oh, it's g to the power of y mod q. That's the extra bit of information that got saved. That's right. And so you know g to the power of y, and remember h is g to the power of x. Um, so we're not, and we raise that to the power of y and then multiplied by our message. Whereas here we have g to the power of y. We're going to raise that to the power of negative x, which I originally questioned why this is two lines instead of just raising c1 to the power of negative x mod q. I raised it to the power of x mod q and then inverted it. But then I remembered, oh wait, that's right. The exponent is an unsigned 32-bit integer, so that literally would have been impossible to have a negative number. So that's fair. But anyways, um, let's see what else. M equals, yeah, so we decrypt our message by taking, we have g to the y, we raise that to the power of negative x, and so we have g to the negative xy, and we multiply that by our thing to get the original thing. Tell me when you've lost me. Anyways, so then the Caesar, which again I just implemented that for fun. You look at like if it's a letter, then you shift it and make sure to mod by 26. And this definitely could have used comments. But if it's not a letter, then you just do nothing. Um, yeah. And then at bash literally doesn't even have an encryption or decryption key because it's literally the same thing every time. It's A becomes Z, B becomes Y, C becomes X, etc., etc. Um, let's see, RSA signature. So signature, you literally just take the string hash, the hash of the message, and then encrypt it using RSA. And then to verify that the signature is correct, you literally just find the string hash, modular the modulo. That's an important step. I'm guessing I must have done that because that issue happened, and then I was like, oh. But basically, you find the hash, and then you take RSA, decrypt the signature, and then make sure they're the same. Meanwhile, ElGamal sign, which once again I'm gonna have to look back at here because ElGamal is so complicated. Okay, so you generate the string hash to compare with the result. Then you generate a random value k, and you have to make sure that k is co-primed to the totient. If it's not, then you try again. And then, what do you do next? Right, okay, so um, you compute the value r, which is generated to the power of k at mod q. And then you also compute s, which is, that's not right. It's, where is it? No, it's not. It's equal to the hash minus x times g to the k at mod q divided by k. Um, it all comes together in the end. Also, I like how this is written specifically because I never had the foresight to write a modular add or modular subtract function. So that's why this looks so complicated, even though it's literally just subtracting two things. But anyways, so S is equal to that, and so the signature is just R and S. And then when we verify the sign, um, what is it? Verify ElGamal sign. Um, we take the string hash, and first of all, make sure that they're within range, because otherwise this doesn't work. Um, and then finally, okay, so we make sure that the generator to the power of the hash is equal to h to the power of r times r to the power of s. And through a bunch of modular arithmetic, we find that they should be equal to each other. Um, because this is equal to, what is it? Oh, raising r to the power of s, since r is g to the k. Then raising, and s is something over k. then r to the s is g to the power of that something, which is the hash minus um, x times r, and this is g to the power of xr, so it works out. Um, anyways, and then plain text signature, you literally just take the hash function of the string, which doesn't really prove anything. Um, you just make sure that the hash is equal to the hash, which anyone could have determined. Um, yeah, I feel like plain text was mostly just added. I think it was added because I just wanted to demonstrate how unsafe plain text is, because you're literally just giving everyone access to the messages you've written, which unfortunately many things still use to this day, like a lot of SMS systems still use plain text. But anyways, so what else? Oh, one last thing. In my last video, the Pac-Man video, I actually forgot to go to the main tab, and I'm not going to forget to do that this time. So what is it? Full disclosure, my code is not in the main tab. It's not the best written, and I knew that going in. Basically, I think the best way to do this, you want to make it reusable so that each case is so you want to make it so that each menu, each thing in the menu and each like possible scenario you can be in is like something that can be. You don't want it to be hard coded. You want it to be so that you could like uh have your own custom set of things right here. And so this is all, yeah. The probably in hindsight, the least I could have done was at the very least make a function that runs a menu like this, make a function that sends a message, which to be fair, I didn't realize until I had implemented the snooping thing after implementing signatures that sending would be something that would be done multiple times. Um, anyways, it is the way it is, and so, but I can explain how this all works. So let's see. First things first, we have so first we initialize the important stuff, such as the list of messages on the public network, um, which menu mode you're currently in, which is set by a long set of enumerated values. Um, the current user, which I think I made this variable before I had made the cur variable, so it's just I don't know. Uh, as well as a few settings. You decide on the encryption method, you decide on the block cipher mode of operation, and you decide if you want to use signatures. We initialize all three users, um, and initialize their encryption method, and we set the current user to Alice. We greet Alice, and then we start running the loop. So we start out in the home menu, and let's see. It displays all the options, and then here is that extra bit of code where it does, if there are any unread messages, it tells us that. Uh, let's see. And then whichever option we pick sends us to a different menu place, except option 9, which ends the program. It ends the while loop. Send a message. So first we ask the message. We have this function called request user, which I'll show in just a little bit. Uh, cancel. That was something that had to be. I'll explain that in a bit. But anyways, receiver. To and from. We get the message, and then after that we say that it's sending. We encrypt the message. If there's signatures, we also give it a signature. We save the original messages, the unencrypted messages, to the user's device, and then we add the encrypted message to the public network, and then it's been sent. And then after that, we make space a delimiter again. So then we read. Um, so yeah, this again, this is very wet code. Um, but anyways, let's just oh, if there are any unread messages, then we display that. We ask who we want to see the messages with, and if we didn't type cancel, then we see the entire conversation. We loop through all messages, which are um, either if it's let's see if it's something if it's to me from them, then we make the header, we decrypt the message, and then display if it's been spoofed unless there are no signatures, and then we display the decrypted contents, and then we also say that the message has been read. Otherwise, the other option is that this message is something that we've saved, and also it was something that we sent to this person, and we have saved on our device. And if so, then we show the saved version instead of showing instead of trying to decrypt a message that we don't know how to decrypt. And then we go back to the home menu. Switch user. This is a very important part of this. Literally just switch to the user though, and greet them, of course. Read raw. It just shows you all the raw messages. Raw encrypted. Keys. Display all the keys. And this part was something that I didn't decide to do until somewhere near the end when I realized, when I look at these keys, I have no idea what I'm looking at. And so I decide, okay, so for RSA, we're gonna label what each component of the keys are. So the modulo and the power, or the modulo and the generator, and H, or just the shift. And also, if we have it set to that option, we will display our own private key. Hacking interface. So, it's similar to the home thing where each thing leads to a different thing. Snooping, where once again we can send a message, but this time we actually get to choose who it's to and who it's from. And also we see, have we, let's see. Oh, sorry, I was thinking of spoof. Sorry, this is Snoop. With Snoop, we look through all the messages. We see, first of all, have we saved this to our device? If so, show it. Otherwise, do we have this person's private key? And that's why it's important that we save our own private key, because otherwise we won't be able to view our own messages when snooping. And if so, then we decrypt it and show it. Otherwise, we just display it as raw content, because what else are you going to do? Spoofing, that's where you can actually set who it's to and who it's from. And I have this nasty bit of way too much nesting probably. But anyways, receiver. We allow spaces. We send it. We encrypt it. We try to sign it if signatures are enabled by basically saying, all right, do we have this person's private key? If so, then okay, do we have this person's private key? If so, then use that to sign it. Otherwise, we'll just use our own private key, and let's just hope no one will notice. And then we save a local copy and push it to the network. And save keys. Very simple. We just save the key. We can't change our own key because well, okay. It wouldn't break things, but it'd be very hard to explain. It'd be very hard to explain. Like why we can't see our messages anymore, the messages that got sent to us while snooping, and it's just, you might as well just make it so we can't save or change our own keys, or change the key that we think we have. There's nothing in here that lets you change your own key, like your actual key. I guess that would be kind of cool, although you'd have to retroactively change all the previous conversations, so that'd be a nightmare. View keys, displaying both the public and private key. Remove keys. Once again, can't remove your own private key. Yeah, there we go. And then we have the math tools, which once again, that's another menu. Factor, totient, discrete logarithm, where there's this very important thing that says calculating. You'll see that in action in a bit. Modular inverse, modular power, multiplication, GCD, LCM, admin thing, where I made sure to adopt the names of the commands that they have in Unix. So for instance, user add, user delete, user del, user mod. SU, you saw that before. That's the switch user command. Anyways. And this was actually where I decided, this was actually what convinced me to add the ability to type cancel to cancel an operation, because I realized when I got to the user delete thing, well, what if you decide I don't want to delete a user? I'm just stuck in an infinite loop now. It's like, well, hold on, you can't delete yourself, and you can't delete a non existent user, and so you're just stuck in a loop and you can't get out of it. And so that's why I added the cancel thing. But also, to be fair, when you try to delete a user, it will ask, "Are you sure?" first. Um, and then, yeah, lots of stuff. Settings. Yeah. So that's basically how. Oh yeah, let's go to request user. So at some point, at the very least, I had the foresight to make a reusable function for requesting the user. So we have booleans. First, the user, or sorry, the list of users, in case you wanted to use this on a different list of users. Um, oh, right, you request user using the cin. But there are also important booleans such as, can this user exist? Should they exist? And are you allowed to cancel? Um, and so yeah, it basically encodes, with these two booleans we encode there should be three cases, but so what is it? Either it needs to exist, it needs to not exist, it can exist but it doesn't have to, or the fourth impossible state, which is it both has to exist and has to not exist. So yeah, but anyways, that's basically how this all works. This was a lot of fun to do. It actually, like, this was one of those projects where just doing it actually sort of reduced some of the stress of the school year just because of how much fun it was. Even though towards the end I was kind of stressed out about not being able to get enough done in time. But anyways, I got 100 on it, and I'm very proud of that. So now let's showcase a few more things. Let's show the ElGamal encryption. Let's show how that's done. So which block cipher mode of operation? Let's do CBC again. And lastly, would you like to use signatures? Absolutely. I am Alice. Let's send a message to Bob saying, hi again. We'll switch roles to Bob. Read conversations with Alice. Yeah. Alright, let's change role to Charlie. And we're going to hacking tools. We're gonna snoop. We can't see what Alice said to Bob, so let's try and find Bob's private key. So let's view keys. We can view the public keys. Okay, let's use math tools. Alright, so what we want is, this is the generator, this is g to the x mod m. So we're going to figure out what g has to be raised to the power of to equal that, mod that. So let's do discrete logarithm. The base is the generator, 812, 816, 834. 812, 816, 834. The number is 140377 4798. And then the modulo is 17306 31677. And it calculating, because once again, this uses like This should be taking square root of n steps but instead it's taking n steps, so it does take quite a bit. Um, and there we go. That's the discrete logarithm. Um, and actually, another part of the reason that I did this, so part of this was to demonstrate, how these things all work and demonstrate an understanding of it. Another part of it, especially with the hacking thing, was one, to demonstrate the dangers of having such a small key, and two, demonstrate exactly how these methods will get hacked into once quantum computing becomes more powerful, so that, like with Shor's algorithm, you can use that to factor large numbers, and um, you can also use it to uh, compute the discrete logarithm as well. And so this sort of demonstrates how exactly we'd use these to hack those specific methods. I also think quantum computing will allow us to break elliptic curve cryptography, but I'm not too sure about that one. Anyways, so we know the discrete logarithm. So let's go back and we're going to save Bob's key to equal 4939 2419. And let's see if that works. It most certainly does. And now we're going to send a message to Alice from Bob saying, "You are a terrible friend." And we're going to go back and change role to be Bob. Oh, sorry, we're going to change role to be Alice. Excuse me. Read conversation with Alice, or sorry, with Bob. "You are a terrible friend." And because it was signed correctly, we have no idea that it was spoofed. All right. Let's see what else we can do. Oh yeah, that's right. I can also send a message to myself, which it's really funny. "Hi me." You might have done that once or twice, where you're sending a message to yourself, like if you need to like transfer files to another device. That's often a quick way to do that. But what I like is, first of all, it tells me, "Hey, there's an unread conversation. Who's it with? Alice." I get the feeling I've already read that, okay? I get the feeling I already read that before I sent it. Anyways, "Hi me." And then what else? The other thing that's funny is that, so if we change roles to Bob, we can view all messages encrypted. Um, Alice sent a message to herself that Alice sent a message to herself that only she can decrypt, and she put it on the public network, and no one else can decrypt it except her. And also, whenever she views it, she's not even decrypting it, she's just looking at the saved copy she has. So it's just completely worthless. And I just find that really funny. Um, what else can you do? Oh, something else I can do. What I can do is I can spoof myself. So who am I? I am Bob. I'm gonna send a message to Alice. Sorry, let's send a message to Charlie. What the heck? From Bob saying, "I am spoofing myself." And since we have our own private key, um, that completely worked. Um, so let's see. We change role to be Charlie. Hey, we finally got a conversation. Maybe we'll finally stop being a hacker because we finally have friends. Um, or maybe not. I don't know. With whom? Bob. I am spoofing myself. Well, you don't look spoofed. But if I change role to Bob and I read the conversation with Charlie, um or sorry, hold on. Um that's right. If I read the conversation with Charlie by snooping, um oh, it still doesn't say that it's spoofed. Okay. Well, that's weird cuz I know for a fact that oh wait, am I Charlie? I'm Bob. Okay, that's weird because I know that whenever I send a message, spoofing it, then I always tell myself this is spoofed, by the way. Um, Whatever though. Oh, that's right. It asks itself, hey, is this the same? Are you the person who sent this, or that this is supposedly sent by? If not, then we say that it's spoof. But because I am myself, then there's no record that I spoofed. In fact, I guess you couldn't even say that I spoofed. I just used the spoof option. Um, oh, and like I said, there's nothing. So we snoop. Let's see. Okay, so as we can see, so Alice sent a message to Alice that we can't read. Um, so what happens if I decide to save Alice's key? But even though I don't know it, I'm just gonna guess it. Let's say Alice's key is 5. Like I said, it has no idea that that wasn't Alice's key. In fact, if it did try and check it, it would have thrown an exception, just trying to compare it. So it's just like, okay, I guess it's 5 now. Let's try snooping with that new quote unquote information. And it says Alice, it gives us a bunch of nonsense. So that's great. Because of course it's using the wrong key. And also because it's using the wrong key, it tried hashing the message and then compared that to, and tried decrypting the signature with Alice's public key and saw, and now it thinks that that message is spoofed. Uh huh. Yeah. Oh, it also thinks that the message to Alice from Bob, the one that Charlie sent, is spoofed. Because it sees the wrong message. Um, but yeah. So and then of course we can remove the key though, Alice's key, and so now that problem goes away. Um, what else we can do is we can spoof to Alice from Alice. Don't you remember sending me? And so we go back and we change role to be Alice. Oh, I got a new conversation from myself. Don't you remember spending me? Well, no, I don't because you're spoofed. But what's funny is if we had Alice's private key, we could have sent it, and it's just like maybe I did send that. I don't remember that though. So yeah, there's lots of other edge cases with this. They're not really bugs per se. They're just kind of funny, I think. Um, but anyways, that's the gist of this. That's how I made this. This was really fun to make. And one last thing I wanted to do. I mentioned with Pac-Man that I forgot to show the main tab, so I might as well show that right now. So, well, eventually it'll open up. Okay, so here we are. And so this was the one tab that I didn't show off. And so it's pretty standard stuff. See, the funny thing is, this is written in processing, which instead of using like the void main function, um, instead it uses setup and draw. And so as a result of that, you kind of have to make global variables because if you try declaring a variable in setup, it's going to be local. It's not going to exist in the scope of draw. And if you try making a variable in draw, well, it'll remake the same variable every iteration. And also it'll be local to that one specific instance of draw. And draw gets called 60 times per second, or actually 60.6060. And this, by the way, on the Pac-Man dossier, this actually is the frame rate that it says Pac-Man runs at. So this is like one of the few times where it's okay to make global variables. Although it's not even global variables per se. These are actually, technically, if you look deep inside the code, these are actually attributes of papplet. But anyways, so we make all these important things such as the directory character, which on Windows is backslash, and on literally every other operating system it's forward slash. We load the font, which I actually was able to find the font they use in Pac-Man. It's Emulogic. We initialize the whole sound setup. We start the game, or we create an instance of the game. This is just for debugging purposes. Anytime I need to directly call upon papplet, because for the most part, papplet should be it should not be called like statically like this. But anyways, this was also a debug, and then we have the list of buttons which we put on. I probably should have encapsulated this better, but we have the list of buttons that we see on the menu screen, the scale. Yeah, that's right. So the thing is, so this is done at a scale. Each pixel is actually becomes for a 2 by 2 pixel grid, and if we wanted, we could set the scale to 3. Would that even work? Would that break everything? It would work, yeah. And then meanwhile, if we set it to 1, then we have this. And also, I like how you can see the characters. They're sort of off screen because they don't show up yet, so they're on the far right. Um, and then now they show up. But yeah, so that's the scale. The scroll just it tells you when you scroll up and down on the menu. We make the size, frame rate, directory character, create the font, create the sound. The artist loads all the sprite. The DJ loads all the sounds. Restart game because that just starts it over from the beginning. Load all the buttons, and then in each iteration of draw, we draw the background. We scale it up. Perform all the updates. Tell the artist to draw the game. Tell the DJ to manage the ambience because during the game you'll hear like wow 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 or wee 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 wee, and so this sort of manages the ambient sound that plays in the background. Um, Oh, we need to have sounds turned off during the demo screen, and so this sort of manages that. Um, and then we update the timer and the mode. Update all the countdown timers, and then finally we animate everything on the game. And don't worry, the animation function knows when to and when not to freeze the animations. Animations? Let's fix that real quick. Animations. There we go. I should update the GitHub. Anyways. Oh, and then we have the key pressed, which literally we map each key to, so WASD or up, down, left, right tells the player to have a new direction. Shift inserts coins. And so we don't measure credits, we measure half credits, because if you have like the 2 coins equals 1 credit, then you have to press shift twice. Um, we determine, and then for some reason, if you insert 99 credits, then it just stops increasing it. I guess they just didn't expect people to put in that many coins, which is pretty reasonable. If you're not, uh, whenever you actually successfully finish inserting a credit, it will play the credit sound. Enter when you're on the credit screen. Should start the game. 2 should start the game, but in 2-player mode. Then we have cheats. Backslash makes you invincible, or enables or disables invincibility. Tab does the rack test. Period places a pack dot right where you are. Sorry, a power pellet right where you are. And then these 4 things are debugs. They display attributes of blinky, pinky, inky, or cloud. Let's see. Mouse button. Mouse is checking the mouse is important for when you press buttons on the pause menu, and then mouse wheel is important for when you scroll up and down the pause menu, and then finally we have a bunch of notes at the bottom. So yeah, sorry for that slight detour. I just felt like that was missing from the last video. Anyways, I hope you enjoyed this. I certainly did. It was fun to reminisce about this, remember exactly how I got everything to work. Um, if there was anything I forgot, then I guess I'll include it in a comment or in the description. But anyways, I hope you had fun. I hope you didn't find this too confusing. And yeah, I'll see you later. Bye.